For the spring, mass, damping, K, spring constant. Then you divide out by M and you get this. You familiar with that? And it's only after you've divided out by the K, by the M, that you're allowed to call this the square of the natural frequency. So omega naught is the natural frequency, the natural undamped frequency. If this term were not there, that omega naught would give the frequency with which the system would like to, the little spring would like to vibrate by itself. Now, further complication is that the visual uses neither of these. The visual uses x double dot plus b times x prime. I think we'll have to fix this in the future, but for now, just live with it, plus kx, and that's some function, again, a function. So in other words, the problem is that b is okay, can't be confused with c. On the other hand, this is not the same k as that. Because this k, to be converted in the, either you have to assume the mass is 1, or you have to divide through by it, in which case. So what I'm trying to say is don't automatically go to a formula one place and make it, assume it's the same formula in another place. You have to use these equivalences. You have to look and see how the basic equation was written, and then figure out what the constant should be. Now, there was something called, when we analyzed this before, and if this has happened in recitation, there was the natural, the damped frequency, I'll call it the natural damped frequency. The book calls it the pseudo frequency. It's called pseudo frequency because the function, if you have 0 on the right-hand side but have damping, the function isn't periodic. It decays. It does this. Nonetheless, it still crosses the x-axis at regular intervals. Crosses the t-axis at regular intervals, and therefore almost everybody just casually refers to it as the frequency and understands it's the natural damped frequency. Now, the relation between them is given by the little picture I drew you once, but I didn't emphasize it enough. Here is omega naught. Here is a right angle. This side is omega 1, and this side is the damping. So in other words, this is fixed because it's fixed by the spring. That's the natural frequency of the spring by itself. If you have damping, if you're damping the motion, then the more you damp it, the bigger this side gets, and therefore the smaller omega 1 is. The bigger the damping, then the smaller the frequency with which the damped thing vibrates. That's sort of intuitive. And vice versa. If you decrease the damping to almost 0, well, then you'll make omega 1 almost the same size as omega 0. This must be a right angle. And therefore, if there's very little damping, this natural damped frequency will be almost the same as the original frequency, the natural frequency. So the relation between them is that omega 1 squared is equal to omega naught squared minus p squared. And this comes from the characteristic roots, of the damped equation. So we did that before. I'm just reminding you of it. Now, the third frequency which now enters and that I'm asking you about on the problem set is, if you've got a damped spring, okay, what happens when you impose a motion on it with yet a third frequency? So in other words, drive the damped spring. Let's X, I don't care. I switch to Y since I'm in a Y mode. So our equation looks like this, just as it did before, except now I'm going to drive that with an undetermined frequency, cosine omega t. And my question now is, see, it's not going to be able to resonate in the correct, you really only get true resonance when you don't have damping. That's the only time when the amplitude can build up indefinitely. But nonetheless, for all practice, and you never have, there's always some damping unless you were a perfect vacuum or something. There's always some damping, so P isn't 0, can't be exactly 0. So the problem is which omega gives which frequency in the input, which input frequency gives the maximal amplitude for the response. We solved that problem when it was undamped, and the answer was easy. Omega should equal omega 0. But when it's damped, the answer is different. And I'm not asking you to do it in general. I'm giving you some numbers. But nonetheless, it still must be the case. So I give you a specific values of P and omega 0. That's on the problem set. Of course, one of them is tied to your tied to your recitation. But the answer is, I'm going to give you the answer, the general formula for the answer, because to make sure that you don't get wildly astray. Let's call that omega R, resonant, the resonant omega. This isn't true resonance. Your book calls it practical resonance. Again, most people just call it resonance and sort of, you know what I mean, Al, type of thing. The answer is very curious, and I would love to have someone explain it to me. Of course, I can derive it mathematically, but that's not entirely satisfying. It is omega R is very much like that. Maybe I should have written this one down in the same form. Omega 1 is the square root of omega naught squared minus P squared. What would you expect? Well, what I would expect is that omega R should be omega 1. The damped system has a natural frequency. Omega 1, the resonant frequency, should be the same as that natural frequency with which the damped system wants to do its thing. And the answer is that's not right. It is the square root. It's a little lower. It's a little lower. It is omega naught squared minus 2P squared.